It was perhaps the wildest off-road drive of them all, and it hadn't started well. A test outing the day before had resulted in a broken steering system, requiring some hasty repairs before the main event. A 7-hour safari with no roads and only 1/6 the gravity of Earth. When astronauts David Scott and James Irwin climbed into their Jeep and set off, they could not have known that 7 hours later their day's work would be described as the greatest day of scientific exploration that we've ever seen in the space program, possibly of all time. They were on the Moon as part of the Apollo 15 mission, and the clock was ticking. Funding was being slashed as the American government had realized just how much money it cost to go to the Moon. NASA was now in a rush. The Apollo 15 astronauts needed to perform experiments originally planned for the now cancelled Apollo 20 mission. The whole program was going to close after Apollo 17. As a result, the remaining astronauts were receiving crash courses in geology. By learning how to classify rocks, they would be able to scout for the most valuable specimens. In addition, the first task at each working site was to set up cameras that could be controlled from Earth. That way, geologists back home could also help them look. The rocks that had been brought back by the first astronauts had been interesting in their own right, but were largely ordinary. Mostly they were jumbled fragments of rocks smashed during the impacts that made the lunar craters. What geologists really sought was something truly ancient that would date back to the Moon's formation. This would help them determine the Moon's raw ingredients, and, by extension, those of the planets as well. If the planets and moons had formed from the collision of smaller rocky objects, as was looking increasingly likely, then the Moon would once have been entirely molten. The lightest minerals would have floated to the top of this global magma ocean and crystallized into rocks known as anorthosites. This was what Scott and Irwin were looking for. So far, however, without any luck. After several hours of exploring, they parked the lunar rover near the rim of a small crater, set up the camera and equipment, and began to scout around, collecting as they went. Scott noticed it first. A gleaming white rock that stood out from the surrounding grey ones. Irwin pronounced it a butte. Scott picked it up and began to clean off the dust from its surface. As he did so, sunlight glinted from the crystalline surface, causing both astronauts to exclaim, "Guess what we just found?" Scott teased Mission Control to Irwin's laugh of pleasure. "Guess what we just found? I think we found what we came for." "Crystalline rock, huh?" said Irwin. "Yes, sir, you better believe it," said Scott, before going on to say that he thought it was something close to an orthosite. When the sample was returned to Earth on the 7th of August 1971 in a splashdown just north of Hawaii, it was swiftly discovered that the rock was indeed an orthosite, almost a pure sample. The press began referring to it as the Genesis rock, assuming that it was a piece of the very first lunar crust. It has been subsequently discovered, through radioactive dating, that the sample does not quite reach back to the 4.5-billion-year-old primordial crust, but crystallized a few 100 million years later, probably in the aftermath of a giant impact that melted a fraction of the Moon's surface. To mark the importance of the find, Irwin had a replica made, which he would carry around in his briefcase or coat pocket as a talking point for many years afterwards. In laboratories behind the scenes, work immediately began on unlocking its secrets, and one thing became obvious. Moon rocks were surprisingly similar in composition to Earth rocks. This was a shock to some researchers because it spoke of a common heritage, that somehow the Moon and the Earth had once been joined. But how? For many decades, the most popular scenario for the formation of the Moon had come from George Darwin, son of the famous naturalist Charles. Drawn to astronomy rather than natural history, George became the Plumian Professor of Astronomy at the University of Cambridge, a post whose statutes had been written by Isaac Newton in 1707. By the time George assumed the chair in 1883, it was a position of privilege. Also, by this time, science was turning its attention to the composition of the Earth. Way back in 1798, Henry Cavendish had measured the world's average density to be 5.4 times that of water, yet it took almost a century for the implication of this work to be acknowledged. The fact of the matter was that the average density of the Earth was almost twice that of ordinary rocks. To produce such a result meant that there must be some far denser material deep inside the Earth. And the only thing that could be was metal. Meteorites had been discovered and analysed that were almost purely iron, and so it seemed reasonable to believe that this and other heavy metals would be found inside the Earth, perhaps forming a central core. Darwin set about calculating how the early Earth would have responded to the formation of such a compact, heavy core. He treated the planet as if it were the now proverbial ice skater, and calculated the way in which the rotation rate of our planet would speed up as the heavy metals sank to the centre of the planet. His work showed that just as the ice skater speeds up when tucked into a more compact configuration, so too would the Earth. Maybe the acceleration was enough, he reasoned, to fling off a chunk of the planet to form the Moon. The idea remained unchallenged until the early 20th century, when a number of planetary scientists began to look at the dynamics of the scenario. As with the formation of the whole solar system, the key factor was the angular momentum, the quantity of the rotational energy stored in the Earth and the Moon. This is a conserved quantity, meaning that it can never change, unless there is an interaction with a third celestial object. So, if you add up the angular momentum of today's Earth and Moon, that must be what Earth alone had before it spat out the Moon. If the Moon's angular momentum were placed in the Earth, it would boost the rotational speed, shortening the length of the day to about 4 hours. As fast as this sounds, it is just not fast enough for Darwin's suggestion to work. To eject part of itself into space, the Earth would need to have been spinning at close to its break-up speed, where the outwardly directed centrifugal force can overwhelm the inward-acting gravitational force. To do that, the Earth would have had to be spinning once every 2 hours, much faster than seems likely from the analysis. Nevertheless, the Moon rocks, including the Genesis rock, were pointing to the fact that the Moon had once been part of the Earth. If that were the case, then they needed to identify something to provide the extra kick, a third celestial body, another planet. Starting in the 1970s, astronomers began using computer simulation in a serious attempt to develop the hypothesis that a Mars-sized body struck the Earth a glancing blow, which threw up a plume of predominantly rocky material that made the Moon. So confident did they grow with this idea that they named the ill-fated planet Theia, after the mythological Greek Titan who gave birth to Selene. The scenario was certainly capable of getting the dynamics right. Not only that, but it also seemed a possible fit to the compositional data. The similarity with Earth rocks was because much of the Earth had been blasted off into space to form the Moon. The slight differences were contamination from Theia. It seemed as if the formation of the Moon was understood, but what no one bargained for was the onward march of technology. It was 2012, and a sample of the Genesis rock had been taken from the Lunar Sample Laboratory facility at NASA's Johnson Space Center, Houston, Texas, by Hejun Hui, a geologist from the University of Notre Dame, Indiana. He reanalyzed it and other moon rocks using modern equipment, and found that they all contained water. This seemed somewhat strange for a rock that was supposed to have formed in the hellish aftermath of a giant impact. The heat generated in the cataclysm should have melted all the rocks and driven off the water. It wasn't the only problem that was becoming apparent. Modern instruments known as mass spectrometers were revealing problems with the Moon's complement of isotopes. These are simply heavier or lighter versions of familiar chemical elements. They are distinguished by the number of particles called neutrons that each element contains in its nucleus. Often they're associated with radioactivity, but this is not always the case. Many stable isotopes of common elements exist as well. The crucial point is that temperature and density determine how easy it is for different isotopes of the same element to take part in reactions. Hence, planets that formed closer to the Sun will display a markedly different isotopic makeup from those that condensed in the colder outer reaches of the young solar system. The isotopic composition, therefore, acts as a hallmark for where the planet was minted. Increasingly precise analysis techniques have now shown that the Apollo lunar samples have oxygen, chromium, potassium and silicon isotope signatures that are indistinguishable from those of the Earth. In the giant impact models, the Moon is made predominantly of Theia. Hence, it should be isotopically distinct from the Earth. In the original analyses, using cruder equipment, there had been enough ambiguity in the measurements to allow for this possibility. However, the message was now crystal clear. The lunar rocks are not just similar to Earth's, they are practically identical. The Earth and the Moon were once the same body. The news set a couple of researchers thinking. Wim van Vestrenen holds a university research chair in planetary evolution at VU University Amsterdam, the Netherlands. His mind started working overtime when his collaborator, Rob de Meyer, a nuclear geophysicist at the University of the Western Cape, South Africa, mentioned deep Earth reactors, or georeactors. This is a controversial proposition, that deep inside Earth, overlying the planet's core, are concentrations of uranium and plutonium that form natural nuclear reactors. If they exist, each one could be a few hundred kilometers across and generating energy. Like many of the planets in the solar system, Earth emits more energy than it receives from the Sun. This surplus powers the magnetic field, volcanoes and earthquakes. By convention, much of this energy is thought to be coming from the natural decay of radioactive elements deep underground. But if georeactors exist, they too will be contributing. Assuming that these natural nuclear reactors do exist, allowed the researchers to imagine an altogether more explosive scenario for the Moon's origin. The pair reasoned that 4.6 billion years ago there was more radioactive material around, because there had been less time for it to decay away in accordance with its half-life. Whenever a nucleus did split naturally, it would eject a fast-moving neutron that could do one of two things. It could either split apart another atom, creating more neutrons and sparking a chain reaction, or, if it struck the right nucleus, such as uranium-238, it could be absorbed, and this would transform the nucleus into plutonium-239. While uranium-238 is not easily broken apart, plutonium-239 is fragile. In other words, such reactions would stoke these natural reserves with more fissile nuclear material, making a big chain reaction increasingly likely. In power stations, this is the way that fast breeder reactors work. They build more fuel than they initially consume. Operators monitor the build-up to make sure it stays within safe limits, but in the putative natural reactors, there would have been no such safeguards. Nothing would have stopped one of them building up so much plutonium that it became supercritical and exploded. To launch enough rocks into orbit to make the Moon would have taken an explosion the equivalent of 40 million billion Hiroshima bombs. Natural nuclear reactors are not as far-fetched as they sound. 16 are known about beneath the Oklo region of Gabon, Central Africa. All are now inactive and were discovered in 1972 by the French Commissariat à l'Énergie Atomique, CEA, which mined the region for uranium. Investigating a significant depletion in the ore of the uranium isotope U-235, the CEA determined that the isotope had been processed as if by a nuclear reactor. Further investigation led to the uncovering of all 16 natural reactors. Each is between 1.5 and 10 meters across, and they were active sometime around 2 billion years ago. They probably continued on and off for a few 100,000 years, kicking out around 100 kilowatts of power until they exhausted their supply of uranium. The hypothetical deep Earth reactors are much larger than those found in Oklo, and instead of the nuclear fuel being concentrated in ore, it will be spread throughout the rocks in minerals such as calcium silicate perovskite. But perhaps most interesting of all, if the georeactors do exist, there may be a way to detect them in the near future. Radioactive decay often releases ghostly particles known as neutrinos, not to be confused with the heavy neutral particles called neutrons. Neutrinos are extremely difficult to detect. They travel at almost the speed of light and interact with hardly anything. Lead shielding with a depth of 1 light year would not even be guaranteed to stop a neutrino, yet detectors have been built. They rely on the fact that neutrinos are produced in vast numbers. Here on the Earth, around 60 billion neutrinos pass through the top centimetre of your thumb and every other centimetre cube of you every second. The detectors capture only the most minuscule fraction of these, but it is enough. The Camland particle detector, based in Kamioka, Japan, and the Borexino detector at the Gran Sasso National Laboratory near L'Aquila, Italy, are both registering a steady stream of neutrinos from the Earth's deep interior. At present, it is unclear whether they are coming solely from the natural radioactive decay of the elements, or whether georeactors are enhancing the release. One way to investigate would be to run a network of neutrino detectors across the world in parallel. It would be possible to coordinate their results and build up a map of the radioactive deposits within the Earth. With this information, it should also be possible to estimate the concentrations and their power output. Reactor regions will give out more neutrinos than natural deposits. Comfortingly, even if natural reactors are found to exist, there is no possibility that one could explode today. This is because the relatively short-lived isotope of plutonium has pretty much all decayed away. The same was not true on the early Earth, say Van Vestrenen and de Meyer. And they point at the Moon as possible evidence. Others are not so sure. Dynamicists have been exploring whether a smaller, faster impacting object could generate the equivalent of an explosion, throwing the Moon into orbit. Another scenario suggests that 2 almost equally sized celestial objects collided and merged to become the Earth, forming a ring of material in the process that became the Moon. Going from a situation where we thought we knew what was going on to one in which all is confusion again has certainly been frustrating. But it is the cycle of science at work. Theories cannot survive if fresh data does not fit. New hypotheses must be found. Throughout the solar system as a whole, composition has been a strongly deciding factor in shaping our theories. But as we start looking at systems of planets around other stars, we are again seeing our original neat ideas thrown into disarray. Within the crucible of our solar system, gravity has drawn sufficient matter together to form the Sun, the planets, the moons, and the various smaller bodies such as the asteroids. Among the planets, one pattern of order seemed so obvious as to scream for an explanation. The planets closest to the Sun are decidedly different from those further away. The solar system splits neatly into two. The 4 planets closest to the Sun, Mercury, Venus, Earth, and Mars, are all similar in the sense that they are comparatively small and mostly made of rock and metal with relatively tenuous atmospheres. Mercury is the smallest planet at just 4,879 kilometers across. Earth is the largest at 12,742 kilometers. The 4 are spread across 500 million kilometers of space, with the Sun at the center of this system. Mars's orbit at 250 million kilometers from the Sun defines the outer boundary. Sun-baked Mercury is tucked just 58 million kilometers away from the Sun, and Earth rests at 150 million kilometers, a measure that is known as the astronomical unit. The asteroid belt comes next, spanning the distance between Mars's orbit and that of Jupiter at 779 million kilometers. There are more than 500,000 known asteroids in this ring of space. The largest is Ceres, at 950 kilometers in diameter. The smallest is about 5 meters, but this lower limit is constantly being extended as better telescopes come online. The asteroids represent the leftovers of planet formation. As we saw earlier, the whole solar system was once a giant asteroid belt, with billions upon billions of asteroids called planetesimals that merged to produce the planets we see today. The asteroid belt was prevented from coalescing into a planet because of the gravity of Jupiter. Sitting at the outer edge of the belt, the giant planet's gravity has corralled the asteroids into more or less orderly orbits, preventing them from touching and growing into a 5th rocky planet. Jupiter has such influence because it is huge, the largest planet in the solar system. Along with Saturn, Uranus, and Neptune, it belongs to the second group of planets known as the gas giants. These are all relatively large, with deep atmospheres surrounding a core of rock and metal. The scale of these planets is staggering. Jupiter is just shy of 140,000 kilometers across, almost 11 times the diameter of Earth. It is enshrouded in an atmosphere that masks the interior from view and contains a hurricane-like storm known as the Great Red Spot, so large that it would engulf our entire planet. Saturn, with its ring system of rocks and pebbles like a mini asteroid belt all of its own, is almost the same size. Uranus and Neptune are smaller, but still they are around 5 times the size of the Earth. Neptune lies at 4.5 billion kilometers from the Sun and defines the outer edge of the known planetary system. There is an appealing symmetry to the arrangement: 4 terrestrial planets in the inner solar system and 4 gas giants in the outer. It cannot help but trigger the feeling that such order must surely imply some underlying principle at work. And indeed, the nebula hypothesis offers a ready solution. With the young Sun in the center of the forming solar system, those parts of the nebula closest to the Sun will have been heated more than those far away. The inner parts of the nebula are heated so much that only the so-called refractory elements, which are resistant to heat, can become solid. These are mainly rocks and metals. The volatile material that needs cold temperatures before it can become solid in the form of ice did not stand a chance. Hence, close to the Sun, planets rich in rock and metal formed: Mercury, Venus, Earth, and Mars. Further away, the temperature became more moderate, and about 5 times further from the Sun than the Earth, ice began to crystallize. It was not just made from water, but also carbon dioxide, so-called dry ice, ammonia, and methane. Together, these are referred to as the astronomical ices. These boosted the amount of solid material available to the forming planets in this region of the solar system, allowing them to become naturally larger. Each planet grew by feeding from the planetesimals in its orbit. The further a planet is from the Sun, the larger the circumference of its orbit. So again, the outer planets had more material from which to grow. These two factors combined to make the outer planets larger than the inner ones. Then gravity really kicked in, because once the outer planets had grown sufficiently large, they generated a gravitational field big enough to pull in gases from the nebula. Gases are the flightiest atoms of them all. It takes a strong gravitational field to hold on to a gas, even one of the heavier ones like oxygen. This is why the Moon, with just 1/6 the gravity of the Earth, has no air. It simply cannot muster the gravitational strength to hold on to the stuff. Earth can retain a thin layer, just more than 100 kilometers in depth, consisting mainly of nitrogen, oxygen, and carbon dioxide. Lighter gases such as hydrogen and helium are virtually absent from our atmosphere. The nascent planets of the outer solar system, in particular Jupiter and Saturn, grew so large that their gravitational fields could retain any gas, including hydrogen and helium, the very lightest elements of all. The only other celestial body capable of doing this was the Sun. So, today, Jupiter and Saturn have compositions that mirror the Sun's, yet neither became large enough to set off the necessary energy-generating reactions deep inside to turn them into stars. In this way, explaining the architecture of the solar system seemed so obvious. It was glorious natural order, springing from nothing more than simple physical laws. Astronomers expected fully that when they developed telescopes capable of detecting planets around other stars, the arrangement of planets in our solar system would be repeated. In 1995, the dream came true. The first exoplanet, the term for such a world around another star, was found. But the dream quickly turned into a nightmare, because nothing was as expected. The discovery of the first planet around a sun-like star fell to a pair of Swiss astronomers, Michel Mayor and Didier Queloz. Based at the Geneva Observatory, they were using a telescope in the Haute-Provence region of France to look for planets. A novel approach was required because planets are so dim compared to their parent stars. It is almost impossible, even today, for a telescope on Earth to distinguish a planet from the glare of its star. So Mayor and Queloz looked at the light from the star to see if it was wobbling. We talk about planets orbiting stars as if the star is the stationary center of the system, the hub around which everything turns, but in reality that's not quite true. The orbiting planet generates its own gravity, and so pulls back on the star. This force is not enough to swing the star into a large orbit, because the planet is much less massive than the star, but it can force the star to pirouette, a motion that corresponds to a small orbit. This means that the star is moving, and so sometimes it will be heading towards us, and sometimes away from us. This minutely affects the quality of the light emitted by the star. Whenever the star is travelling towards us, the light is squashed and its wavelength shortened. On the opposite side of its pirouette, the star will be moving away from us and its light will be stretched to slightly longer wavelengths. This is a manifestation of the Doppler effect, one of the most powerful tools in the astronomer's arsenal for diagnosing the celestial realms, simply because it betrays a celestial object's movement towards or away from us. The time it takes the star to complete a pirouette is revealed by the sequence of stretching and squashing in the light, and is equivalent to the time it takes for the planet to traverse its orbit. Once the planet's orbital period is known, the diameter of its orbit can then be calculated, so the planet's distance from its star is revealed. Combining this with the magnitude of the squashing and stretching in the star's light then gives the planet's mass. In 1995, Mayor and Queloz had a puzzling signal. Applying the analysis suggested that they had found a planet around the star 51 Pegasi. But in comparison to our own solar system, nothing made sense. The planet was a gas giant, at least half the mass of Jupiter, yet it was far closer to its star than Mercury, which completes an orbit in 88 days. 51 Peg b, as the new planet was termed, shot round its orbit in just 4 days. It is so close to the star that its atmosphere must be a searing 1,000 degrees Celsius. Since the heat a planet receives drives its storms, 51 Peg b's atmosphere must be a maelstrom. All in all, this newfound world seemed an unreal place. So unreal, in fact, that doubts were raised about its very existence. All uncertainty was swept away within weeks when an independent American group analyzed data they had been sitting on. 51 Peg b was found there, too. More than that, they announced other planets around other stars. Gas giants could indeed be found in close proximity to their parent stars. In one fell swoop, astronomers had found not just a new planet, but a new class of planet, and swept away the belief that gas giants could only be found at large distances from their host stars. According to the theories of planet formation, designed with our solar system in mind, this was impossible. There was simply not enough matter that close to a star to build a gas giant. So, said the theorists, 51 Peg b and its ilk must have formed far from the star, and then migrated. The theoreticians set to work on wondering how planets could move about, and found it easier than they expected. A planet moving through its orbit feels no resistance, because there is no air to drag on it. So, in principle, a planet could circulate indefinitely. Back during the birth of the planets, this was not quite true. The proto-planet was ploughing through the remains of the cloud that collapsed to form the star. This could have provided a drag that set a large planet spiraling inwards towards the star. En route, its mighty gravity would have scattered the interior planets into wild orbits, or even pushed them to a fiery death in the central star. The more the theoreticians have looked, the more possibilities they have found for this kind of behavior. At the same time, the more observers have looked, the more types of planets and arrangements they have found. There are now more than 1,000 identified exoplanets. Nearly 200 multiple planet systems have been revealed. And one thing is becoming very clear: our solar system, with its orderly collection of 4 terrestrial planets and 4 gas giants, is not normal. Far from it. Instead of being the norm, it may prove to be the exception to the rule. The only way we will know is for astronomers to continue developing more and more sensitive spacecraft for detecting smaller and smaller planets. There are a number of missions being readied for launch that will do this. NASA is building the Transiting Exoplanet Survey satellite, TESS, for launch in 2017. ESA is working on the Characterizing Exoplanets satellite, CHEOPS, also for 2017. And the Planetary Transits and Oscillation of Stars, PLATO, for 2024. These will reveal whole solar systems, not just the larger planets. It will truly allow us to see if any patterns emerge, or whether we are just living in an oddball system of planets that just happens to be nicely arranged. But before astronomers get completely carried away finding planets around other stars, it is perfectly possible that there are additional planets around our own sun, waiting to be found. Maybe there is even a whole new solar system out there in the icy depths beyond Pluto. My phone rang as one day was about to turn into another. It was the last moments of Friday the 29th of July 2005, and my first thought was to ignore the call. It could not be a family emergency because it was the office phone that was ringing. I had well and truly finished work for the week, but something made me pick it up. "Hello?" I deliberately sounded a bit vague. It was Stephen Young, the publisher of Astronomy Now magazine. I was the editor of the magazine at the time, and Steve lived and worked in Florida, so I was used to him being in a different time zone, but even so, this was unusual. "It's midnight," I said. "I know, but NASA is about to announce the discovery of Planet 10. Since the discovery of a new planet in our solar system had not happened since 1930, I was prepared to work some serious overtime. Minutes later, I was hooked into a hastily arranged press briefing in which Mike Brown of the Californian Institute of Technology described the discovery of a distant world larger than Pluto. My grip tightened on the telephone. The implication was clear. If Pluto was a planet, so was this. 2003 UB313 was the official designation, but as the press quickly picked up on, Brown and his colleagues Chad Trujillo and David Rabinowitz jokingly referred to it as Xena, after the heroine in the television series Xena, Warrior Princess. Almost instantly, the name of the planet became the central story. As discoverers Brown, Trujillo and Rabinowitz had the privilege of choosing it. Brown had originally wanted to call the world Leela, a concept taken from Hinduism that can be used to describe the cosmos as the outcome of the divine being's pastime or sport. It was also close to the name of his newly born daughter. But before any naming could take place, the International Astronomical Union decided it was finally time to define what was and wasn't a planet. Until this point, there had been no definition. Most of the planets in our solar system were known since antiquity. They were the wandering stars, visible to the naked eye. On top of these, only 3 more planets had ever been discovered in orbit around the Sun. The first, Uranus, was spotted by William Herschel from his back garden at 19 New King Street, Bath, England, on the 13th of March 1781. The second, Neptune, was bagged by Johann Gottfried Galle and his student Heinrich Darré of the Berlin Observatory on the 23rd of September 1846. In Herschel's case, he was conducting a systematic search of the night sky. Galle, on the other hand, was working from a predicted position of the planet given to him by French mathematician Urbain Le Verrier. Then in 1930 it was the turn of Clyde Tombaugh from the Lowell Observatory, Arizona. On the 18th of February he found the planet Pluto as he compared photographic plates of the same region of the night sky. He noticed that in the 6 days between the photographs, one object in the field of view had moved. The discovery made headlines across the world, but it soon became obvious that Pluto was not as mighty as the other planets. Follow-up observations showed it to be a minnow. It has a diameter of just 2,300 kilometers, making it smaller than our moon. Its volume is less than 1% of the Earth's, meaning that it has a total surface area equivalent to that of Russia. Could such a comparatively small object really be called a planet? The question was moot until the discovery of 2003 UB313. Now a decision had to be made because astronomers were on the hunt for more of these objects. The International Astronomical Union set up a committee of 7 individuals under the chairmanship of Owen Gingerich, a Harvard University historian of astronomy. The committee also included the best-selling science writer Dava Sobel. Together they drafted a proposal for planethood. In August 2006, the International Astronomical Union met in Prague for its biannual General Assembly. It was a fitting place, as this was where Johannes Kepler first met Tycho Brahe and began the work that led to the mathematical description of planetary orbits. The committee's draft proposal was put before the membership. It said that 2 conditions had to be met for a celestial object to be deemed a planet. First, it had to be in orbit around a star, while not itself being a star. This was not contentious. Stars must be large enough to generate their own energy by means of nuclear fusion reactions. This is what makes them shine. Planets, however, appear bright because they are reflecting starlight. The second condition was that a planet must generate enough gravity to be capable of pulling itself into an almost spherical shape. This would be the case for an object with a mass of around 500 billion kilograms and a diameter of about 800 kilometers. In this way, the committee hoped that they were using the strength of gravity, hence the natural laws of the universe, to underpin the definition. But there was a price to pay. It would require the reclassification of several solar system bodies. The largest asteroid, Ceres, would now be a planet. Pluto's moon, Charon, would also be a planet, making the two a double planet system. Together with the 9 traditional planets and 2003 UB313, that would mean the solar system contained at least 12 planets. The committee pointed out that astronomers knew of a dozen other asteroids that further observations could prove were also planets by this definition. It proved too much for many astronomers because it required too much upheaval in the way we thought about the solar system. Just 2 days after the draft resolution was published, amendments started to be proposed by the membership. Eventually, after heated debate and some acrimony, things came down to the wire. It was the last day of the conference before the IAU executive put forward the amended definition for vote. A crucial additional clause was added. To be considered a planet, the object must have cleared the neighborhood around its orbit. This would rule out the smaller bodies, such as Pluto, because they share similar orbits with other celestial objects. Pluto, for example, is the largest of the Plutinos, a group of asteroid-like objects that have been corralled into similar orbits by Neptune's gravity. It would mean that the solar system consisted of just 8 planets. Pluto would be part of the newly defined class of dwarf planet, along with 2003 UB313 and a retinue of other distant little worlds. Of the 2,700 astronomers that had attended the General Assembly that year, fewer than 500 were still there on the last day. Nevertheless, the vote went ahead and revealed there was overwhelming support for the amended definition. The die was cast, and Pluto was demoted from planet to dwarf planet. Instead of becoming only the 4th man in history to discover a planet, Mike Brown became the first to cause the demotion of one. He embraced the infamy, calling himself Pluto Killer on Twitter, and writing a book titled How I Killed Pluto and Why It Had It Coming. When it came to the official name for 2003 UB313, Brown and his colleagues proposed Eris, the Greek god of chaos, strife, and discord. It was accepted, rather appropriately, given the dispute its discovery had sparked. For now, the controversy had quieted down, but there are reasons to believe that a whole host of additional bona fide planets are orbiting the Sun at extreme distance, and that the next generation of survey telescopes will find them. It comes down to the way planets were built, in the series of collisions between smaller objects called planetesimals. To simulate this process, astronomers develop computer models that track the growth of the planets. These show that in the inner solar system there were probably 20 to 30 Mars-sized planets that grew into the 4 terrestrial planets Mercury, Venus, Earth and Mars. In the outer solar system, the same simulations show that there were probably a similar number of planets, but this time about the size of the Earth. These coalesced into the cores of the giant planets Jupiter, Saturn, Uranus, and Neptune. In other words, about 4.5 billion years ago, the solar system contained around 40 to 60 rocky planets that fought it out for supremacy, ingesting their rivals and growing into the planets we see today. With this dog-eat-dog scenario in mind, astronomers have taken to referring to the situation as the oligarchic scenario. Computer simulations by Scott Kenyon at the Harvard Observatory show how it would have taken place. Initially, the oligarchs kept to their orbits, circling the sun as if sizing each other up. Periodically they drew close to each other, and their pull of gravity caused subtle changes in the shape and size of their orbits. These changes built up until suddenly things went out of control. A chaotic period ensued, in which oligarchs were flung all over the solar system. Many collided and coalesced to become the familiar planets of today, but not all. Near misses were as likely as collisions, and according to the computer simulations, a near miss between an oligarch and a burgeoning gas giant planet could be enough to throw the smaller object into exile. Some would be given so much of a kick that they would have broken free of the sun's gravity. Even now, they will be wandering the galaxy as frozen planetary orphans. Most of the exiles won't have made it that far. They will remain in the sun's gravitational grip, forming a cloud of planets that loop the sun in giant orbits, taking between tens of thousands and millions of years to complete. They will be found in orbits 25 to 250 times further from the sun than Pluto. And because the gravitational kick given to these oligarchs alters the size, shape, and orientation of their orbits, they will be scattered at random angles to the original disk containing the rest of the planets. It is impossible to know the precise numbers of worlds that might be lurking out there. But Kenyon's simulations suggest that between 10 and 20% of the oligarchs suffered this fate, meaning that between 6 and 12 Earth-to-Mars-sized planets are waiting to be found. If true, it is the equivalent of a whole new solar system's worth of planets. There could well be circumstantial evidence for this population already. Unlike the rest of the planets, which spin more or less at right angles to their orbit, the seventh planet, Uranus, spins on its side. This gives it an extreme version of the Earth's midnight sun or polar night phenomena. On Uranus, the night can last for decades, followed by decades of daylight as the planet crawls around its 84-year orbit. But what could tip a planet on its side like this? Perhaps it was a collision between the gas giant and a speeding oligarch on its way out of the solar system. The only way to be certain whether these extra planets are really there is to see them. Despite their size, that is a tough undertaking, because they are going to be very faint indeed. The sunlight needed to make them visible will be feeble at such distance. Compounding the problem is the fact that the gravitational scattering which sent the planets out there in the first place is a chaotic process. This means it robs astronomers of any way to predict where the planets are likely to be hiding. The only way to search for them is to trawl the whole sky using telescopes, and this venture is so time-consuming that it is way beyond the scope of most observatories, which usually allocate time to astronomers in chunks of just 2 or 3 nights. But the search may be receiving a boost from a new project called the Large Synoptic Survey Telescope. To be sited on Cerro Pachón, Chile, LSST is scheduled to begin work in 2024. With a mirror measuring 8.4 meters across, it will be roughly 10 times as sensitive as anything available today for such surveys. Calculations show that it could detect an Earth-sized planet up to 500 times further away than our own planet is from the Sun. The telescope will be a monster that devours the sky. Its wide-angle camera can survey the entire visible sky in just 3 days, and then go back and start again. Every night it will generate 30 terabytes of data, enough to fill the hard drives of several hundred PCs. Automated software will detect moving celestial objects in this ocean of data and post the coordinates on a public website for others to follow up. Although professional observatories will be working hard to stay on top of the follow-up observations, the public nature of the data opens the door for amateur astronomers to discover a new planet in the solar system. Would-be planet spotters should keep their eyes peeled for unusually slow-moving faint objects in the data, preferably far away from the orbital disk of the solar system. So, if you fancy going down in history, all you need to do is wait until LSST fires up, then get ready with a telescope, an internet link, and an awful lot of patience and good luck. Yet, no matter how many new planets may or may not be awaiting discovery in those far-flung realms, it is in the centre of the solar system that we find gravity's true crucible. This is the Sun. In terms of matter content, the planets are mere trivialities. The Sun contains 99.8% of all the matter in the solar system. All 8 planets, the dozen or so dwarf planets, the many dozen moons, and the billions of asteroids and comets, put all of these together, and you will still only reach 0.2% of the total mass in the solar system. Since mass is all that really matters when it comes to generating gravity, the Sun is by far the gravitational hub of the solar system. Its gravity extends into the far reaches of space, shepherding comets out to 50,000 times Earth's distance from the Sun, and it contributes to the overall gravitational field of the galaxy, together with the other 100 billion or so stars that make up the Milky Way. Gravity works inside the Sun as well. The weight of the overlying layers bears down on the core of the Sun, creating a pressure more than 250 billion times that experienced in Earth's atmosphere. This ratchets up the temperature to more than 15 million degrees Celsius. Under these extreme conditions, new atoms are forged from old. Hydrogen is fused in a series of nuclear reactions to become helium. In the process, energy is released, and this is the principal definition of a star, that it shines by making its own energy. To keep the Sun shining, it must convert about 4.2 million tons of matter into energy every second. This energy is what becomes sunlight, but it takes hundreds of thousands of years for it to fight its way out through the crushing weight of the surrounding gas to reach the surface of the Sun, 695,000 kilometers overhead. Once there, the light speeds off into space, crossing the 93 million miles to Earth in just 8 minutes. The extraordinary truth is that the sunlight rising from the eastern horizon every morning was generated inside our luminary before any human walked the Earth. But to deduce this required a leap of faith in the way that science is practiced, and opened the door to the models that would rise to dominate cosmology.